Hello, everyone. My name is Malcolm, and I am a civil engineering master's candidate at Concordia University. Today, I'm presenting research I've done with Dr. Mazdak Nik-Bakht and Dr. Amin Hammad on exoskeletons for the construction industry. I'm going to speak about the background that informed our research objectives, how we designed a realistic controlled test to evaluate exoskeletons for the rebar trade, and the results of the initial implementation of the realistic controlled test. And finally, what we intend our future work to be. In a 2019 survey, 46% of U.S. construction workers reported having back injuries, knee injuries, shoulder injuries, and other musculoskeletal disorders during their careers. We see similar trends in other studies, and particularly in the rebar trade, which has a high rate of life-changing lower back injuries. So occupational exoskeletons, or OEs, are a promising solution for preventing these kinds of injuries. OEs are designed to support different areas of the body, so back support, shoulder support, full body. And OEs are also defined by their structure being rigid or soft, and by their actuation being passive, which means reusing energy in the biomechanical system of the human body, or active, which means they add energy to that system. So here's a framework from Van der Beek et al., which is an ideal process for developing ergonomic interventions like OEs. The process starts with understanding injury statistics, ergonomic risk factors, and the physics behind these risk factors, all to inform the development of an OE and its evaluation. An iteration happens when the OE design needs to be improved based on the evaluation. Ultimately, the goal is that the OE is effective, we implement it at a large scale, and we observe a reduction in the injury rates in a population of workers. Within the evaluation stage, there exists two kinds of evidence. Efficacy, which is beneficial results in laboratory conditions, and effectiveness, which means the OE actually prevents injuries in real working environments. So to summarize the most important points of our literature review, here's why realistic, trade-specific, standard efficacy tests are important. Efficacy is important because OEs need to be safe, iteratively improved, and compared in the same controlled environment. Tests need to be standard to acquire benchmarking data, and tests need to be trade-specific to represent the variable and intense construction tasks and environments which are not yet represented in the existing body of standards. Finally, test conditions need to be realistic, because if they're not, then efficacy will not actually be a good predictor of effectiveness. So realistic trade-specific efficacy tests do already exist for some construction trades, and these tests are moving towards being standard, which is great. The gap in the research, however, is that more trades need to be represented by these kinds of tests, including the rebar trade. We collaborated with a Montreal-based exoskeleton designer and producer called BioLift Technology, and by the time we started collaborating with them, they had already iteratively improved their OE design based on subjective feedback from rebar workers. To place this collaboration in context of the framework I just described, BioLift had already addressed all the first 5 steps of developing an intervention, even iterating their design based on subjective evaluation. Our goal, or the scope of our research, just lies within this evaluation stage, and specifically in the efficacy evaluation stage, so the laboratory evaluation. Based on this background, our research objectives are, first, to design a realistic controlled test for evaluating back support exoskeletons for rebar workers who are installing slab reinforcement, because this is a very common construction project for basically most buildings and bridges need to have slabs be constructed. Second, our objective is to implement this realistic controlled test and to analyze the results. So we designed our test based on 3 of the 4 fundamental ergonomic risk factors, which are force, repetition, and posture. So based on these risk factors, these exist in the very common tasks of lifting, carrying, placing, and tying rebar. We looked at video evidence, and we consulted with experienced rebar instructors to verify that the conditions of our test were realistic. The design of the test course, in which the 4 tasks are to be performed, looks like this. So there's a lifting, carrying, placing, and tying area. In groups of 2, participants lift 4 rebars, they carry them over an existing matrix, and they place the bars. Then they tie every other intersection, and this completes 1 round of the test course. 6 rounds completes the entire test course and takes about 1 hour, and participants tie 150 intersections in total. We determined the load to be lifted, carried, and placed using the NIOSH Composite Lifting Index. This was to make sure that it was safe for all participants. And the chosen value was also verified to be realistic by the experienced rebar instructors. Participants' opinions are measured using 3 surveys, one on perceived effort, one on discomfort, and a more general survey regarding perceived support, range of motion, obstruction, and usability. The effects of the OEs were measured objectively using 3 types of sensors. Local effects are measured using electromyography for lower back muscle activity, which I'll talk about more in the next slide. Global effects are measured using heart rate, and posture and joint angles are measured using inertial motion capture. Here's a brief demonstration of how the BioLift OE reduces peaks in lower back muscle activity during a participant completing a simulated version of the task in the test course. So here 100% comes from a maximum voluntary contraction test. And you can see as the participant lifts, carries, and pretends to place rebar, their peak in muscle activity was reduced during the lifting task. And this is a proxy for a large peak in force in their lower back muscles. And similar results are shown in the tying task. So the test was implemented at the Steel Trades Training Center in Montreal. As you can see by their morning warm-up session, they already have an awesome health and safety culture at the center. And in the same room pictured as the last slide, we collaborated with the center to implement the test course. So here you can see 2 participants wearing the OE in the middle of their second round of tasks, as well as the 3 areas designated for lifting, carrying, placing, and tying. Most participants completed 4 days of testing. Here you can see examples of the participants completing the 4 tasks, and also the tool pouch and tie wire reel used for rebar work that's integrated into the Exoskeletons tool belt. There were 9 participants in total, 8 of which were divided into 4 groups, and their mean age was 27 years with a standard deviation of 10 years. And all participants were men or male at birth, so in future implementations, we hope to involve women students and professionals to reach a gender balanced sample. There are lots of positive opinions regarding the OE, as represented by the dark and light green cells in this figure. The 2 oldest participants thought the OE made them feel unbalanced during the carrying task. 1 participant felt overheated by the OE. There were some constructive feedbacks regarding obstruction and mostly positive results regarding usability. Lower back discomfort decreased on average, and discomfort at the OE contact points was very low. And this is a good result because contact point discomfort can be seen as a potential short-term measure of the potential long-term undesirable effects of the passive OE, displacing forces in the body. There's almost no change in perceived effort in the OE condition compared to the control. And we believe that this is due to a limitation in the experiment design. So this is future work to investigate effort and fatigue further. For the tasks of lifting, placing, and tying, there were significant reductions in peak and in average muscle activity, like was shown in the video earlier. And this is probably a difference of risk factors in the lifting and placing task versus the tying task you can see in the figure. For the tying task, we noticed some unexpected differences in posture. So we decided to investigate this further. Most participants used a wide tying stance, which is typical of experienced rebar workers and recommended by the experienced rebar instructors, and a minority of participants use a narrower tying stance, which is more typical of less experienced or novice rebar workers. Our preliminary results suggest that because of these differences in tying posture, novice workers may benefit from a back support exoskeleton more by reducing their lower back muscle activity, while the wide stance of experienced workers, however, it puts them at risk of decreasing the stability of the passive structure of their lower back. So in other words, the intervertebral discs and ligaments of the lumbar spine. And so experienced workers may therefore benefit more from the OE by maintaining the stability of the passive structure of their lower back. And in this way, OEs may have different benefits depending on a worker's experience level. So in conclusion, we successfully designed a test towards the goal of realistic trade-specific standard efficacy tests and successfully implemented it at a steel trade school. We analyzed the results and found significant reductions in participants' lower back muscle activity, as well as positive opinions about the OE. And based on this initial implementation, our future work involves improving the test and collaborating with ASTM to contribute to a future standard. Our future work also involves implementing the test with all the sensors proposed in the test design. And as shown in these figures, we started to do so in a pilot field study. You can see a person in the field tying rebar here with all 3 types of data represented. Thank you very much. I appreciate your time.